Welcome, everyone, to Day 5 of the Spring 2021 Martin Gardner Celebration of Mind Talks. I'm your host, Bob Hearn, and we've been very fortunate. We've had a bunch of incredible talks so far, and we have a bunch of incredible talks still to come. Today, I'm very pleased that we have here Catriona Agg. Catriona teaches math in England and has developed quite a large Twitter following for her incredible felt tip pen geometry puzzles. If you've not seen them, then you are in for a real treat. And I'm really looking forward to this talk because she's going to deconstruct the process a little bit by which she comes up with them and show us the tricks. So let's begin.
It turns out that coming up with a good puzzle is really hard, which is possibly not that surprising. A nice way to start making puzzles is to think about kind of puzzles that you've seen that you like. So I'm going to do that a bit. I think the one that I mentioned in the abstract, which some of you might have seen before, is the area of an annulus. And this is a really classic puzzle, but I think it's amazing. If you haven't seen it before, you're probably thinking, what on earth is an annulus? In fact, it might be you have seen this puzzle before, but you don't know what an annulus is, so I should say a bit more about that. Here we go. This is a circle. I know it doesn't look like one, but I've said it is, so it is. This is another circle. These two circles are concentric. They share the same center. Again, they might not look perfect, but because I've said it is, now in your head, this is metamorphosed into some incredible perfect diagram. Now, an annulus is this region in here. Let me color it in. It's the donut. And the incredible thing about this shape is that we can find this area, which you'd think like straight off, well, there's two shapes. I can find the area of each circle. You know, you think you do the big one minus the little one, right? And to do the big one, you're going to need to know its radius, and to find the area of the little one, you're going to need to know its radius. But the incredible thing about an annulus is that you can find the area of the shaded orange region here with just one measurement. For example, this measurement across there, if I told you that that was 12, that line I've drawn all the way across, that would be enough information. Now, the first time that I saw this, I remember being kind of amazed by it. Possibly you've seen this so many times that this doesn't amaze you, but maybe you can remember the amazement. That one measurement is enough. And what that means is that this annulus has the same area as any other annulus where we can draw a line of length 12 across. So this one, or if I drew like a mega one, that's so big I can barely fit on the page, but if I can draw a line of length 12 across it, then that whole kind of annulus would have the same area. So it's only that measurement. The actual kind of relative parts don't make a difference. Do you not think that's amazing? I think that's amazing. Of course, why does it work? Well, it works because of Pythagoras' theorem, and probably some other things as well, but I tend to use Pythagoras' theorem to solve it. So let's draw this in again. So what did I say we wanted? I said that we wanted the radius of the big circle, let's call that R, and the radius of the little circle, let's call that S. That's an S. I know it's a bit tiny. And then what do I want? Well, I want this area minus this area. But of course, I could just factor out. And that area there, well, I've got R and I've got S And if I know anything about tangents, I know that this line here, which was half of my 12 that went all the way across, so 6, it's going to be at right angles to those. So I've got my little right angle triangle. And that means that I know r squared minus s squared is, well, 6 squared. So we've got 36 pi. Now I think that that's pretty cool. And I love the sort of invariance that you get from this. But so this is quite a classic puzzle. I'm guessing lots of people have seen this sort of thing before. What I really want to do is talk about kind of where we might take this. So given all that, what might we do with it? So I'm going to show you a couple of, I don't know, kind of adaptations of puzzles that are based on this. So a few of them are mine, a few of them aren't. Let's start with one that's not this one. I saw this from brilliant.org, who come up with lots of nice things. And it's a semicircle. And it's another semicircle inside that. And they drew a line across the middle, and I can't remember how long it was. Let's call it 12, since I've decided that's my new favourite number. And the question was, what is this yellow shaded area? I'll leave you to have a little think about that, but if you want to put a hint or a potential method in the chat, feel free. I will come back to it, but in the meantime, I'm going to draw another puzzle. Which one should we go next? Let's try this one. How about a quarter circle instead? Okay, so that's a quarter circle, and I'm going to stick another circle inside it. And I'm going to draw a line across it. How long should I make the line? Let's say 12. I hadn't planned to make everything be 12, but you know, why not? And I would like us to find this kind of green area in here. I'll tell you what, let's stack up a few semicircles. Actually, no, let's do quarter circles first. So here's a quarter circle. Here's another one inside it. And here's a third one. So I've got 3 quarter circles all kind of stacked up there. My question is that if I tell you that this area here is, should we say 12? Can you please tell me what is this area? What's this little area? Let's do a different puzzle. What can we have? Maybe we should only do one more. No, I'll go back to the earlier ones. I'm going to phrase this puzzle slightly differently. I'm going to phrase it as, which is the larger area? Is it this purple bit, which is split into 2 parts, or this red bit? So which is larger, purple or red? So there's kind of 4 different puzzles, but very kind of, I don't know, all based off the same idea. I've just seen someone post in the chat a version of the original annulus puzzle phrased as carpet laying, but kind of in the shape of a ring. And I've definitely seen this puzzle posed really nicely as laying a carpet around a pillar, because of course if you've got a pillar right in the middle, then that means you can't ever measure all the way across like you might want to. So this kind of tangent line is the only way that you might possibly do it. Yeah, that's such a nice way of doing it. Right. Let's have a look at some of these then. So how is this related to the first one? Well, if I slide this across, now it's worth thinking about why I can do that, but this little white semicircle, I can just slide it backwards and forwards, can't I? Because, well, it's not going to change the fact this horizontal line. nothing's really going to change. The total area is going to be the same, although it's kind of changing shape slightly. So given that I can slide this backwards and forward, I'm going to slide it right into the centre. And when I slide it right into the centre, well, it's like I've got exactly half of this shape. And so I've reduced it to exactly what I had before, but now I've only got half of the area I had. So what did I say it was before? I'm not that interested in numerical answers, to be honest, but I feel like I ought to follow this through. Oh yeah, I said 36 pi. So it would just be half of that, 18 pi. This one is slightly harder. In fact, I probably should have put that last because this was a bit cruel, but a nice way to think about this one is that a quarter circle with a particular diameter has exactly the same, a quarter circle with a particular radius has exactly the same area as a circle with that diameter. You can do a bit of work to prove to yourself that that's true, but if you're convinced that that is true, then that means that I could replace this white circle with a quarter circle, and then of course I can just slide this around, and why don't I slide that right into the middle? Well, then I've got exactly the situation I had before, but I've only got, well, first of all, the 12 is actually now sort of double, but also I've only got a quarter of it. And I think those two effects are probably going to cancel each other out. At the very least, I can see a route to a solution, so I'm pretty much okay with that. This one here, now this is a nice one, because at this point we start saying, well, how is that different to this one? We said before that we could measure what this shaded area was by drawing in a line. Now they were horizontal before, but I'm going to make it vertical now. The length of that line is important, and actually what am I doing with that line? I'm squaring it. Well, so I might as well turn it into an area if it's going to be squared. There'll be a factor of pi in here as well, but actually the factor of pi is exactly the factor that I wanted. It turns out that this black quarter circle I've drawn in has exactly the same area as the shaded dark blue part. Well, that means that both of these, because one is this middle extra section plus 12 is this little middle extra section plus what I wanted, so they've got to be the same. And you can use a very similar argument, just with a bit of sliding this backwards and forwards to prove that one's the same. It sounds really silly, but basically most of the puzzles that I post on Twitter are variations of a single one. So by starting with something like this, you can post loads. I've posted so many variations of this, and people every time are like, oh, that's really cool. Because it is really cool, because it's not my puzzle originally. The original fact is the really cool bit. And I just sort of play around with it. I'll show you another one. That's part of my goal here tonight, by the way, is I know lots of people are here because they follow me on Twitter. And occasionally people are very nice and say, oh, your puzzles are amazing, I love them so much. And I'm sort of here to show you that they're not really all that, but it's very nice, you know. Do keep being kind to me because I do enjoy it. Right, let me show you another puzzle that I first saw on Twitter. I saw this because someone posted it at, someone put it up on the screen at a maths teacher conference, and a maths teacher took a picture of it and posted it on Twitter. And it was like this. It was two squares. One has side length X, one has side length Y. And within these two squares, a triangle has been drawn that looks a bit like this. So there we go, we've got a triangle. And the question was this: find the area of that triangle in terms of X and Y. Now, I'm just going to talk quickly about how I did this, but you might want to ignore me for a few minutes and try and work it out yourself. What is the area of that triangle in terms of X and Y, the side lengths of the squares? Well, I did this by a lot of algebra, really. I worked out what the total area of the two squares was in terms of X and Y. X squared plus Y squared, that's fine. I then worked out that I could find this little white triangle in this corner. I could find this little white triangle up here, and this big white triangle down the bottom, and take all three of those away. And I did a huge amount of cancellation. And if you do all of that, well, I was very surprised when all of that came out. And it turns out the area of this is half y squared. It doesn't depend on x at all. That was a big surprise to me, I'll be honest. I was not expecting that at all. I'll say that I just told you that story about how I started doing all these geometry puzzles in the summer of 2018. This would have been about March 2018, I think I saw this. So it's well in advance of me actually making any of my own puzzles. But then I thought it was so cool that I took it and showed it to a friend of mine over coffee on a Sunday morning. I sort of grabbed a napkin and scribbled this on it and passed it over. And you know, and I was sat there feeling fairly smug as he dived into the same algebra that I'd done, and he was working all of this out, and it cancelled down to half y squared. And I was like, watching all this happen, knowing it was going to. Said, oh, isn't that really cool? He goes, oh yeah, that is really cool. And then he said, oh yeah, of course it is, because I can just shear this triangle along the top of that triangle along this line. Here's the base of the pink triangle. Its height is the perpendicular distance from there to here. Well, I'm just going to imagine sliding it down. And if you do that, of course, you're keeping the base the same. The base hasn't moved at all. You're keeping the perpendicular height the same because you're moving it all the way down this parallel line, but you end up sliding that point all the way down to here. And it now looks like this. Well, of course it's half y squared. Of course it doesn't depend on x, it just ends up sitting completely inside y. Now that was a bit of a mind-blowing moment for me because I got to half y squared, being very pleasantly surprised by this, but hadn't really thought to go any further. And then this was the kind of realization that actually there's a geometric side to this as well. So yeah, once I started making puzzles, one of the very first ones I made was something to try and use this fact because it remained one of the kind of coolest things I've seen. So I'm going to show you a few more of these. And one of the reasons that I really like these puzzles are that you can sort of do them in your head. So here's one that I made that has sort of been, I don't know, I feel like this one's got quite popular. I've seen it in a few different places. So it's 4 squares. And then I'm going to draw in a triangle. What colour should we have? Let's have a green triangle that goes from here to here and then all the way up to the top. Now I've drawn that a bit badly because it looks like that triangle goes through this point here, but it doesn't have to. You can make this 4th square as big or as small as you like. For example, this will still work. Oh no, it still looks like it goes here. Oh, never mind. This is the danger with not really preparing slides in advance. Never mind, I enjoy drawing things. Here's a different puzzle that also uses 4 squares. This time, rather than a triangle, I'm going to join up several of the points. So this is a quadrilateral in here. Just to make it clear, the points that are on this quadrilateral are this bottom corner, this corner in here, this corner in there, and obviously that bottom corner down there. So that's quadrilateral that I've shoved in. Here's one where we've got 3 congruent rectangles. So this one is a little bit different to the others. This one's actually completely determined. There is only one possible size of congruent rectangle where you can do the following. Draw a line from there to there to there. It does go through this point. And then draw a line up like this. My question here is that if I tell you that each one of these congruent rectangles has an area, say, of 9, can you please tell me what the shaded area of that triangle is? You can use a similar idea. And should we add one more? Yeah, let's do this one down here. Here's another one. I did a version of this one for a bell ringing magazine because, and I made up a nice little story about it being about spotlights shining onto a church tower. So maybe you can sort of see that. This one is a little bit more complex, but the question is this: out of these two little spotlights, which area is greater? Is it this yellow total area or this orange total area? So there's four, no, is that 4 different ideas? Yes, because I drew one of them twice. 4 different ideas based on the same puzzle that I saw. This first one, hopefully you've had a little bit of a chance to think about it. This first one's really nice. You might spot that once again we've got diameters of the square. What am I talking about? Diagonals of the square that are parallel. So I can slide this point all the way down to the bottom. The nicest thing about this though is that when I do that, now at that point, I guess I could draw the square in, but it will be gone. Once I've slid this top point all the way down to the bottom, it just looks like this. Now you could actually at that point sort of work it out in terms of, oh, I forgot to tell you, let's say this has area 9, one of these little squares. You could at this point work it out, or you could do the same trick again, because now we could say this is the base of the triangle and slide this point all the way down to the bottom, and what we end up creating is basically this little triangle in here. That is exactly half of this central square. I think that's really clever. So it's sort of 2 lots of shearing will work there. Oh yeah, this is called shearing. I call it triangle sliding, but it's not called triangle sliding. It's called shearing. Triangle sliding sounds cooler. The pink one, you might have had a chance to find this one. I think if you split it in 2, you can do quite nicely. Do I want to split it in 2 like that? No, not at all. I've just made my life a lot harder. I wanted to split it in 2 like this. You see, sometimes I forget how to solve my own puzzles. The third one, now, the first thing to do here is convince yourself that the only way that this can happen is if this point actually lies directly above that one. Because once you've decided that that's true, you can slide things around pretty much as you like. In particular, you can, if you chop it off here, you can slide this point along to fill up half of this 9 rectangle, and then you can, well, happily convince yourself if you've realised that this does kind of follow on, that that's also going to be half of the one above, so you end up with an area of 9 in total. And those of you who have ever followed me on Twitter will not be surprised to know that the answer to the which colour is more is that they're exactly the same. There's a nice little step you can do here. So if you consider this one that contains this triangle that contains the 2 yellow parts, you can imagine sliding this along and it filling up half of the big rectangle. But the nice trick that you can do is you can show, because of these 2 lines kind of emanating out of this point, I don't know if you ever studied sort of vanishing points and things in art, but you only get that effect when you've got similar shapes. So because we've got this kind of vanishing point down here, goes through the corners of these 2 rectangles, it means the rectangles themselves must be similar. If they're similar, then they have parallel diagonals, and we can end up basically shearing this lower orange triangle downwards along here, and also filling half of the large rectangle. That was a very quick run through a lot of things. So I am going to stop because I hope I've at least convinced you that the process of coming up with a puzzle is not some magical black box. It's about finding a relationship or a puzzle you like and trying to adapt it in some kind of fun way. If you want lots and lots of puzzles drawn with slightly more care and attention than the ones I've done today, you can follow me on Twitter. That's where you can find me. If you have a favourite shape, please feel free to hang around and tell me. And if you have any questions, I'm happy to stay and answer some.
Thank you, Catriona. That was absolutely delightful. It's you say it's not magic, but it seems like magic as you're describing it. You've just shown us some of the tricks. So we've had lots of great comments and discussions in the chat. So, okay, here's a question from Arthur. How do you go the other way, though, from the original toward the more unusual puzzle? Do you just try adding new squares wherever?
Yeah, that's quite a good question. Yeah, pretty much. This is kind of the same idea, but I wanted it. Yeah, how can I hide this? I think that's a good way of thinking about it. I find a nice relationship that I want to use. And obviously I don't want to completely plagiarize what's been done before. So I try to find a way to hide that relationship within a larger picture, which generally means adding a few more new squares, or kind of a new arrangement. So yeah, I'm trying to kind of sneak it in where someone might not notice it straight away.
We have a request to show a shearing in slower motion.
Shall I try and do this pink one that I got wrong before? That would be fun. And I'll draw it bigger. That's the main thing. Although I realise that's a bit like, you know, someone doesn't understand you, so you say the same thing again loudly. But I am just going to draw the same diagram again, but bigger. Right, so what did this puzzle have? It had 4 squares. Okay, one was on there, and then one kind of filled in the gap. How big does that need to be? Kind of like that. They look, oh goodness me, they looked sort of square on my paper and not on the screen. Never mind, they're squares. And I said I was going to join this point to that point to that point, like that. Okay. Now, this is potentially embarrassing given that I didn't do this right the first time, but I'm going to split this into 2 different triangles across there. I'm going to consider them separately. So first of all, let's just consider this kind of little orange triangle up here. So I'm going to just kind of pull that out. Did I say orange? I was going to colour it in orange and I never did. Right, here we go. So this triangle, because its base I'm going to consider as this diagonal, its perpendicular height is the distance from this diagonal. If you imagine this actually is the base, it will look more like your traditional base and perpendicular height. And so any triangle with that base and that perpendicular height will have it the same area. For example, triangle with this base that goes to that point there. So by shearing, I sort of always picture the triangle itself actually like this point picking up and moving along this line. But really it's just saying that the area is going to be the same if I draw in this triangle. So this top part here actually has the same area as half of that top small square. I can do a really similar thing now with the other parts. Here, if I consider this as the base, then its perpendicular height is going to be that distance there. Turn it around again to make it kind of look clearer, but anything with that base and that perpendicular height is going to have the same area. So in this case, probably consider this part in here. So from all that, I can show that the area of the original pink quadrilateral is actually the same as half of the area of the small square plus half of the area of the big square. And you can do a bit more algebra with that to kind of show where that kind of how that fits in with the other squares in this relationship. But that's the interesting bit of the puzzle for me, so I'll stop there. Hope that helps a bit.
Very nice. Do you only draw, or are you also cutting and moving shapes of paper around when you develop a puzzle?
No, I don't cut things out, because when I actually draw, I don't draw in on paper. I draw in like a big book, so it's all kind of stays in. It's a bit too zoomed in to be able to see this, but basically, yeah, this is my book of stuff that I draw
Very
in.
cool.
So yeah, there's not really an opportunity to chop things up.
So Dora Schatzschneider asks, do you ask your students to solve these puzzles?
Occasionally. They've got pretty good at knowing some of the tricks, so I tend to give them adapted versions of the puzzles that say things like, prove that these two areas are equal, because otherwise they just sort of guess their favourite. If I say what fraction is shaded, they just start guessing nice fractions rather than actually doing any maths work. Yeah, I don't use them hugely, actually. They are mostly for me. They're mostly because I enjoy them.
So here's a great question. I had the same observation during your talk. For puzzles based on invariance, it's often possible to cheat by arguing, well, if this puzzle has a fixed answer, then I can calculate it in a degenerate case by moving the circle over to where it's radially symmetric or whether. Is there a name for this type of cheating?
I don't know, but I completely agree with you. It's very satisfying type of cheating, isn't it?
It is.
Like it's very nice to say, you know what? Like, what if that circle got so small it wasn't there anymore, and then I just had a single circle with diameter 12.
Yeah.
And of course, it does still work. Yeah.
Yeah, it's not cheating if you know that there actually is an answer. Or sometimes in these pencil and paper puzzles, if you know there's a unique answer, that means you can rule out some branches.
I think for puzzles on Twitter, some people will ask on Twitter, oh, am I cheating if I do this? Like, you're solving maths on the internet for fun. There is no cheating. If you're having a good time, then that's fine. But I do really like the fact that you can build an idea of what you think the answer is, but then there's that second level of, if you do care about these things, then you're motivated then to go on and prove that is always the case, rather than just for a couple of special cases.
Do you use some kind of software like GeoGebra to investigate these relationships?
No.
Oh, okay.
Not unless, well, so I draw everything by hand, in part because I'm not very quick at using things like GeoGebra. And also, if it's that complicated that I can't solve it by hand, then I'm not that interested in it as a puzzle. There are some really difficult puzzles that I don't know how to solve, that you could construct and kind of answer, but I don't know. I really like the simple cases, and that generally means that there's not too much algebra, so I can do it by hand. I think there was one puzzle I've made where I had to use the cosine rule, and I felt a bit dirty about it, but in general, like, the ones that I like best are actually the ones that I can do in my head by imagining rearranging different bits.
Yeah. Are you worried about running out of core identities? Are there plenty more to build puzzles from?
Oh, all the time. But luckily, I do keep discovering more. I didn't really know that much geometry when I started doing this, to be honest. Like, I've discovered loads of circle theorems and stuff that I never learned at school. So yeah, I'm pretty sure I'm a long way from being an expert. There's a lot out there.
So John Miller says, I like the way you stand back and give subtle hints or not as people are first seeing a new problem. Do you have any rule about that? Also, do you call these problems, snacks, or what?
I call them puzzles. Do I have rules about it? No, only that, I mean, it's very difficult, isn't it, when you're talking to your own computer to know what's going on in people's heads. But it does seem to me like it takes a while to absorb a puzzle. And I don't particularly like silence, but because it feels really awkward on my end. I'm aware that if I was actually trying to give you proper time to solve the puzzles, I would have probably let you have some thinking time and silence. But at least if I kind of move on and then loop back, you've got some time to think about one of them rather than think about four, or just admire the pretty pictures of all four puzzles. Because I think that's fine too. And that's another reason I like geometry puzzles. You can kind of admire them without having to dive in and solve them, which is nice, I think.
How often do you have to buy new pens, and which color runs out first?
Black always runs out first.
Mm.
Yeah, that's an easy one. How often do I buy them? It depends. These pens that I really like that I have at the moment are this is my second set this academic year since September, but that's because I use them at school as well. So most of my teaching that I do is in fact doing exactly what I've done here, like writing on paper and projecting it up on the wall for my students to see me do. So they get a lot of use outside puzzle making too. These pens, which a colleague bought me as a Secret Santa present, they've lasted for ages. These are really good. So I've no idea where they came from, but yeah, they're really cool.
Do your students create their own puzzles inspired by yours?
Very occasionally, yes. And I think it's really cool. Yeah, occasionally a couple of my students will then send me a message with, oh, I made this puzzle. Or sometimes I made this puzzle, but I don't know how to solve it. They've sort of come up with quite a cool construction, but they don't know how to actually work it out. So that's quite nice. It doesn't happen very often, but it's happened a couple of times.
Here's an interesting question. Have you thought about the volume between two nested spheres? I wonder if there's something similar there. I mean, it sounds like it would be more complicated.
Yes, it does, doesn't it? I have a really hard time visualizing 3D shapes. I like things I can draw. But I mean, there is that really cool, and I guess it must be related, puzzle about the napkin ring, where you've got kind of a sphere with a cylinder drilled out to it. Do you know what I mean?
Yeah.
So, yeah, I don't know.
So a comment, two spheres work the same way if you use the radius of the tangent disk. Really? Wow.
Very nice.
Okay.
Thank you for that.
So someone suggests you should run a regular geometric puzzles column like Alex Bellos does in The Guardian. I think that would be an excellent idea.
It would be really cool, wouldn't it? Unfortunately, I'm not very good at coming up with puzzles regularly. So I go through sort of spates. In March, I kind of had a puzzle pretty much every day. For the last few weeks, I've had no new ideas, so there have been no puzzles. The thought of having to actually stick to a deadline is a little bit horrifying. And I also get very impatient. So if I make a puzzle, I post it straight away. Or I have a limit of one per day, actually. I try not to post more than one puzzle per day, but it's rare that I come up with more than one puzzle on the same day anyway. But yeah, like waiting weeks for it to come out in print would be, well, for a start, I'd forget how to solve it by the time it came out.
This has been our best attended talk so far this week.
Oh.
You have a lot of Twitter fans.
Brilliant. And, thank you, everybody, for coming.
Yeah. So thank you, everyone, for coming, and thank you very much, Catriona. That was delightful. And
thank you. Thank you for inviting me.